This is a study on a project that we did for the Seattle Municipal Tower. The project was done in 2008, and so the numbers and data you're going to see are in regards to the year 2008. And it was a pretty exciting project. The tower was located on the 14th floor of the Seattle Municipal Tower. It used to be the key tower. So the original goals of the project, it had a lot of different criteria that were driving what we were doing up there. Primarily, we wanted to look at saving water with a fluid cooler system to minimize the plume hitting the building. So this is down on a pedestal on the 14th floor, but right adjacent to it is viewing glass of the 16th floor and up. And they have an existing cooling tower down there where they had to put a cowling on it to try and blow the discharge off the tower away from the building to avoid that plume hitting the building. So they were very sensitive to this issue of plume coming in against the building. Also, they wanted to add ability to do the water side economizer per the Seattle Energy Code, and also looking at redundancy to the cooling system. This project actually entailed the addition of another condenser water riser system to feed process heat pumps that were serving data center loads within the building, and they had to take care of that. Also, they wanted to look at electrical savings, and also they wanted to explore chemical savings with non-chemical tower treatment for this particular loop. So the original basis of the design focused on looking at up to 50% water savings, to looking at space and weight constraints versus a dry cooler scenario. They were considering, because of the plume issue, going with the conventional dry cooler scenario. The problem with that is you couldn't get water side economizer in certain dry bulb conditions. And anyways, they were also looking at 10 units to do the equivalent load. So it would have been a very large footprint on the roof, which was over a swimming pool, actually. So it posed some pretty good structural issues, adding more weight to this roof. The final footprint we were looking at was 28 feet long by 8 feet. This was the original tower design at the time. And looking at electrical savings and, again, the non-chemical water treatment. And this is a schematic of what the tower looked like. Basically, you had two fluid coolers attached to each other side by side. That's why it was so long, 28 feet long. And you had a dry side on this region over here, and you had a wet side on this side. And it was piped in series, so it would always go first through the dry side and then into the wet side. Overall, the project was projected to save over $21,000 a year. These are 2008 numbers, not taking into consideration escalation in utility costs. And it was composed of a variety of things. There were other things going on in the system with some new heat pumps being put in, so there was electricity savings associated with those. The fluid cooler also had a lower static pressure, so it had a lower horsepower than the tower that they were looking at. And then on the water side, because this is such a new application of the technology, we had to defer to the manufacturer to help us out compute the water savings for our particular environment, and then applied a safety factor to that. And that's because of the heat exchanger design. It's very proprietary, so you have to work with your manufacturer to find out what the performance is. And then the other category, that included some of the chemical savings projections, but also some other maintenance issues that we were correcting at the time, and was a blend of some other items there. So problems encountered along the way. I believe at the time this was done, I think this was the first wet dry tower done in the United States. It was certainly one of the first ones. It was The biggest issues were on the control side of the tower itself. They had a Sage panel that they had. The intention was to run a VFD that would shunt between the dry side and the wet side as needed. So it would do, it'd be at 0 at no load, go 0 to 100 on the dry side, and then it would shunt over to the wet side. Drive would go to 100% on a constant drive, it'd bypass the drive, and then on the wet side it would go 0 to 100 based on the condenser water set point. We found that the wet side was getting engaged more than we had originally anticipated, and this was primarily due to the condenser water set point itself. So we had to make some adjustments there and put in a reset schedule to make sure that we are optimizing the dry versus the wet. So then, this was the old schematic of what it looked like. It was like any other fluid cooler, only 2 of them stuck together. But the one dry side, it truly was dry. It was 2 dry coils, and then going into the wet side. Another issue we had was the coil at the time was coming from Italy, and they had some interesting differences in pressure rating expectations that we had to address in the design, and by chance we got damage in the shipment. So that added some issues to the project, but that was repaired and taken care of. The controls were the Sage Generation 1, so they were still working out at the factory how the controls were going to work, and this had a very large footprint, 28 feet long, 8 feet wide, and it was just very sizable. So where is it going now? Now Evapco has redesigned the tower pretty significantly. When you look at the tower, it looks like their conventional induced draft tower, kind of the box design with the fan on top. And most of the sizes have just one fan, so you don't have to worry about shunting between 2 different fans with different VFDs and things like that. In the larger sizes, they do have 2 fans, but they're already on the 3rd generation of the controls, so they've learned a lot, much with this project and I think a few others around the country that have since gone in, and they've been able to get the footprint down smaller, which is always a plus. The single fan, and that is on a VFD. And also they've added now spiral fins at 3 fins per inch on elliptical tubes. So they've been able to compact the number of fins within the tower. So one of the reasons they're able to shrink the size of the tower and also increase the efficiency of the heat transfer because of the addition of the fins. And then you only have a single VFD to deal with per motor, which is a plus. It has 2 different options now currently. You've got either a tower like the previous here. This is one version where there is a single pump for the outside fluid side, and it runs in either a dry mode or in a wet mode, similar to a fluid cooler might be able to be programmed on your own. But again, you've got the added efficiency because of the coil development. Or you could get one with, there's actually a baffle that cuts down the middle of the tower, and it still is the same shared sump, but the air streams are now completely separate. And you can actually run the entire tower can be run completely dry, as this diagram is showing, or you can run a single side wet and a single side dry, or you could run the entire thing wet. So what are the challenges with the newer technology? As I'm seeing right now, I think there's not many left. They do tend to be more expensive than your conventional towers, obviously, but that's pretty indicative of fluid coolers. You have heavier equipment versus dry coolers, but again, similar to other fluid coolers. But depending on the selection, usually the hybrid towers are now smaller and lighter than a wet-only tower of the same capacity. It is still a developing technology. There aren't many around the country, but I think it's definitely a promising technology that is really worth considering, especially that we're considering water now as a resource that we need to figure into the calculation. Before, it used to always be electricity and gas, and that's all we really talked about, but now more and more water is becoming acknowledged to be the rare resource it is, and it's becoming more expensive because of that. The benefits with this style of system, you have less water consumption. Typical projections are in the 40 to 50% water savings range. Of course, it's going to depend on your environment and where your wet bulb is and where your dry bulb is in your environment. In general, this type of tower has a smaller footprint versus other wet towers. You have a less plume potential, so especially when it's colder outside and plume is a greater risk, you can shut down the wet side and run entirely dry and you have no plume, just like a dry cooler. So that's very nice to see, especially in Seattle, in a dense metropolitan area. The manufacturer is continuing to improve their software and helping with selection and performance. You also have increased evaporative capacity, also dry capacity, because of those fins that they've added to the tubes. Fortunately, they have moved that production within the U.S. So the coil is no longer made in Italy. It's now being manufactured in the U.S. So that's also an advantage for that. You also have less horsepower even over the first generation. Because of those efficiency gains in the heat exchanger, you can save power on your fan because of lower stack pressure. Also, when you're in dry operation, it's a lower stack pressure load on the motor than when you're running water over it. And then it's the most water efficient system type available of this type of fluid cooler. So that was just a very quick overview of the concept of a hybrid wet-dry tower. Are there any questions at this point?